All right, so here we are on Chapter 4, Analyzing Change and Applications of Derivatives, and this is Section 4.7 on related rates. So related rates, well, many situations in the world can be modeled mathematically, and we'll see in this section you can look at salt coming out of a container and making a pile. We can do the baseball fields. We can do volumes of snowballs. There's a lot of different things we can look at mathematically, and calculus is going to help us analyze the changes that are taking place, whether it's a snowball melting or how much what the rate of change is for the salt coming out of the container or whatever it is. We're going to see that we can use calculus to help us solve these. Now, the rate of change of the output variable of a continuous function is often affected by a change in the input variable, and sometimes that rate of change of the input and output variables interact with respect to some third variable. So if you think about the size of a snowball, it's going to be the volume of that snowball, and that's going to be changing basically your radius, and there's going to be a time involved, how long it's going, and there's going to be the volume changing. But if you think about the volume, that's an equation that only includes that radius. It doesn't include time, but time affects it, and so that third variable is what we're thinking about there as far as our time. Now, this is kind of another similar example here with the circle. So it's called interconnected change. So we have some equation relating the volume of a spherical balloon, or like a snowball, and that volume is 4/3 pi r cubed. So when our balloon is inflated over time, we're inflating it, it's getting bigger, it's getting bigger, getting bigger. The volume increases. Well, as the volume increases, what's happening? Well, our radius here is also increasing. So we might start little, we have a small radius and get bigger as time goes on and gets bigger and bigger and bigger. And so even though our V and our R depend on how long it's been since we started to inflate the balloon, we don't have time involved in our function here. So what we need to do is we're going to look at an equation relating the change in volume with respect to time and the change in the radius with respect to time. And what happens is it's going to be our change in volume with respect to time is equal to 4 pi r squared change in respect of radius with respect to time. And what we've done is we've taken the derivative of both sides. And when we take the derivative of this side with respect to time, that gives us dv dt. And when we take the derivative of this side with respect to r, what happens is that 3 comes down, and then we have that becomes a 2, and that 3 cancels. So we have 4 pi r squared, and then dr dt. Okay. So that's how we're getting the time involved, is because it's going to change that volume with respect to time, change that radius with respect to time. So this is going to be some rate, this is going to be a rate, and this is kind of the equation that's kind of left over from our original equation. Now, with related rate equations, we have the df dx and say dg dx, okay, where f and the g are the dependent variables, and that's in respect to the third variable, which is independent, and that's our x. So, a lot of our problems we're going to do, we might have a dv dt and a dr dt, and so the time is that third independent variable, whereas the volume and the radius are dependent. Okay, so that's going to be kind of how we're looking at this. And if we forget how this all works, it's all based on our chain rules. So, we have our df dx, which might be looking like this. Well, that's just df dt times dt dx. And maybe we know we can figure out the dt's, and that gives us then a df dx. And then we have, the f prime of x equals f prime of t times t prime of x. But really the key is this here part. And we'll see that here with the related rate equations. They're basically, like I said, they're forming them by differentiating both sides of the equation with respect to time, and that's usually the case in this one. And so the differentiation always requires this chain rule, and so we also sometimes have to use a product rule because we might have something like 6a ln of a, and we'll see that equation here in a little bit. And we have to use the product rule. We have to take the derivative of the first times the second plus the second times the derivative of the first, and go from there. And so we'll have to use that product rule. And so here's a really basic, simple example, linear type of equation. And what we want to do is we want to find a relation dp dt and dx dt. And how do we do that? Well, we're going to look at this and we're going to find out, well, our p and our x are dependent variables, and it's t is going to be our independent variable. And so what we're going to do is we're going to take the derivative of both sides with respect to t, and we're going to do it with on p on the left and with x on the right. Okay, so we're treating p and x as functions of t. And again, what it says is we're differentiating the left side of p with respect to t. And because p is a function of t, its derivative is just simply dp dt, because what we're doing is we're taking derivative with respect to t of p. Well, that just becomes dp dt, because with respect to p, that just becomes p to the 0 times 1, and that just is just 1. And so we just have dp dt. And then on the right, we do the same thing, except now we have 39x plus 4. And so when we take this, it's a little more involved. So our variable x is the function of t. So if we do this, this is how we're going to initially write it, kind of like we did with the p. But because we're taking it with respect to x, what we're going to do is we're going to say, well, we'll take the derivative of this with respect to x times the derivative with respect to t of x. And what happens there? Well, we'll take this derivative, which is kind of what we did up here, but it was all kind of in steps here. And so the derivative of that, well, the x goes to 0 because this can bring down the 1. 39 times 1 is 39. And the 4 goes to 0 itself. And then we just have dx dt. And so that would be what this piece is going to. So we can, we're going to just say d dt of 39 plus x. But when we get done, it's going to look like this. And what we know is we're taking the derivative of what's inside of here with respect to x, and then we're putting dx dt at the end. And that's why we're doing that, because the way when we do this, that's the derivative, we get this, then we have dx dt like this, and that gives us our last piece here. So what does that give us? Well, that's the right side. We found that dp dt, either way we look at it, is on the left. And so that is an equation relating the two rates, the dp dt and the dx dt. Okay. All right, so when we actually get to word problems, application problems, however you want to look at it, what is the strategy for solving these problems? Well, first, we need to identify the variables. So we're going to have independent variables, and we're going to have dependent variables. Now, there's only going to be one independent. Usually it's going to be with respect to, so it's usually, again, time. And dependent variables, that could be the volume, the girth of a tree, all kinds of different things that we can have there. And then step 2, we're going to write an equation relating the dependent variables. Now, the independent variable may or may not appear in our equation, so that's something you're going to have to realize, that you might end up with, area is equal to pi r squared. And so there's no time in here, but it's because that's the independent variable. Okay, so that's going to be the key. And then we're going to differentiate both sides of the equation we found, so maybe this one, with respect to the independent variable to produce a related rates equation. So we're going to take the derivative of this respect to t of a, and then derivative of this respect to t of the r. And so what we're going to get is something out of there. Then what happens, we'll have, two rates. We have a dA dt, and that's going to be equal to 2 pi r, and then dr dt, and then we can use those rates here and solve for whichever one's the unknown. Maybe we know this one, we know r, and we can solve for the dA dt. What is the area changing with respect to time? How is that happening? And so we can find that, and that'll be how we can solve the problem. All right, so let's stop there, and then we'll come back with actual examples.